Hey everyone, in this video I will do token classification by fine-tuning a BERT model, and for the model I will choose these BERT based uncased. This is like one of the most popular model in the Hugging Face repository with a download last month of 33 million. And then I will apply this fine-tuned model to predict my tokens, that is NER tokens, that is named entity recognition tokens, on these dataset CON-LL 2003. So this dataset is the summary of this dataset is written right here. The shared task of CON-LL 2003 concerns language independent named entity recognition. We will concentrate on 4 types of named entities: person, location, organizations, and names of miscellaneous entities that do not belong to the previous 3 groups. Shared task data files contain 4 columns separated by single space. Each word has been put on a separate line and there is an empty line after each sentence. So let's look at the dataset right here. So this is the train part. I have 4 columns: NER, post tags, chunk tags, and NER tags. And these are the tokens. And then I have a POS tags, that is positional tags, then chunk tags and NER tags. So what is a token classification task? This generic task encompasses any problem that can be formulated as attributing a label to each token in a sentence, such as named entity recognition or NER, where we find the entities such as persons, locations, or organization in a sentence. This can be formulated as attributing a label to each token by having one class per entity and one class for no entity. Then I have POS, that is parts of speech tagging, where we mark each word in a sentence as corresponding to a particular parts of speech, such as noun, verb, adjective, etc. And lastly, chunking, where we find the tokens that belong to the same entity. This task, that is chunking, can be formulated as attributing one label to any token that are at the beginning of a chunk, which are called B dash, that is beginning of the chunk. Then attributing another label to tokens that are inside the chunk, which is attributed as I dash, and then a third label which is O to represent tokens that don't belong to any chunk. And here are the main tokens, the way it is represented. O means a word does not correspond to any entity. B PER or IPER means word correspond to the beginning of or is inside a person entity. B-ORG or I-ORG means a word corresponds to the beginning of or is inside an organization entity. Then I have B location or I location, just similarly like the previous one. And then B miscellaneous and I miscellaneous means a word correspond to the beginning or is inside a miscellaneous entity. Alright, with that introduction, let's start the actual coding for these fine-tuning tasks that will be the subject of this video. So initially you have to install all these libraries: pip install transformers, datasets, tokenizer, seq-eval, and these are just regular libraries that you have to definitely install for any Hugging Face related or transformer related project. Alright, and then I need to import all these libraries, that is dataset, numpy, then the relevant modules from transformers. So here I'm importing BERT tokenizer, data collator for token classification, and auto model for token classification. And the dataset we are using is CON-LL 2003, and that's why I'm doing datasets.load dataset. And then here I'm just printing the dataset, and this is Hugging Face dataset dict. So this is the structure it follows. So I have 3 segments: train, validation, test, and within each segment I have the features, which are ID, which is a unique ID, and then 4 feature columns, actually tokens, post tags, chunk tags, NER tags. And for the number of rows, I have 14,042 for train, 3251 for validation, 3454 for test dataset. And if I print shape, that's how it will be printed. And that is, you will see the exact shape that it has. All right, now I'm going to print an actual train element. 2003. Yeah. I'm taking it from the train. and that is the actual element. And if you compare it with the actual dataset, you can see it matches exactly. So the ID is 0, which is what you got, 0. Then for the tokens, you reject pause tags, chunk tags, NER tags, and that's exactly what we got. So this actually prints the first row of the dataset. Okay, now what I'm going to do, just print the NER tags. So features, NER tags. So that's how you will get the feature names. I have name as names as 0, B person, I person, B org, etc. From the dataset, you can also get some metadata. So you can do something like this: description, and that will give you the entire description that we saw in the Hugging Face data official page. The shared task of CONL 2003 concerns language independent named entity recognition. So that's exactly what we saw in the official page. Yeah, so now I think that's enough about the introduction of the data. Now let's define my tokenizer. BERT tokenizer fast, that's what we imported. And now we will apply this tokenizer to tokenize an example input from the dataset and see a particular problem which we need to solve before proceeding the fine-tuning model building. So I'm just tracking the first row's value from the trained dataset, and the tokenized input will be tokenizer. To that I have to pass example text and tokens. Towards equal to true. And here again, I took the tokens because that's the column name of our dataset. As you can see right here, this is a con LL 2003 dataset, and token is a column name that I'm interested in. And the tokens will be tokenized input. Actually, no, tokenizer dot convert IDs to token. Tokenized input, input IDS. I also need the word IDS. Now let's print the length of the example text NER tags and the tokenized input IDs. So what I mean is, let's run this cell first. Okay, let's print this right, and also I just want to print the length of the NER tags in my example text and the length of the tokenized input IDs. And as you see the problem here, and the problem is that this is called the problem of subtoken. So the input IDs returned by the tokenizer are longer, that is 11, length is 11, versus the labels that our dataset contains. And our dataset contained the NER tags of only 9 of them. And why it is happening, to understand that, you need to understand first that the transformers are often pre-trained with subword tokenizers, meaning that even if your inputs have been split into words already, each of those words could be split again by the tokenizer. This means that we need to do some processing on our labels because the input IDs returned by the tokenizer are longer than the list of labels our dataset contain. And this is mainly happening because some special tokens might be added, for example CLS and separator token, and then because of possible splits of words into multiple tokens. Now, to align these, to resolve this problem, we need to depend on these word ID methods. And we can see the output of this word ID is that it outputs a whole list, and all these elements, that is which are not none, that is the same number of elements as our processed input IDs. But then the special tokens, that is at the beginning probably it's a CLS token and at the end it's probably a separator token, the special tokens are mapped to none. And based on this output of word ID methods, I am going to resolve this. And in the Hugging Face official documentation also, they propose a similar kind of solution to resolve the situation of special token being mapped to none. And the strategy for the solution is like this, that here we are going to set the labels of all special tokens, that is which are mapped to none, to -100, because the -100 is the index that is ignored by PyTorch during training. And the labels of all other tokens we will be mapping to the label of the word they come from. And so that's pretty much the strategy I will follow in my next method. So this function method name is tokenize and align labels, and this function mainly will have two jobs, that is set -100 as a label for those special tokens, and then number two job is mask the subword representation after the first subword, and then we align the labels with the token IDs using the strategy we just talked about. So this method will take my example, which is a dataset, and another Boolean argument. Tokens. Again, I'm choosing tokens here because that's what our dataset has. True, and is split into words true as well. Yeah, so that's my tokenized input. Okay, I just forgot to mention another thing when I was explaining this problem here, that the problem we are trying to solve here, which is the input IDs returned by the tokenizer are longer than the list of labels our dataset contains, which is this. Our list of labels the dataset contains is 9, but the input IDs returned by the tokenized input is 11, and that's a problem we are trying to solve with this method. Now, before, if you want to see that why these 9 became 11, how these special tokens got added, which we saw that special tokens are mapped to none here when we are printing these word IDs, but to see the actual tokens, you need to see these output of this tokens variable, because that's why I defined this tokens variable, and you can get the tokens by applying this method convert IDs to tokens on the tokenizer, and that's what I did in the tokens variable. I'm just running it here again and printing my token. Yeah, so that's the reason I got 11. So you see that all these inside they are number 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's the number of NER tags we have in this particular data element. But a two special token they have been added at the beginning and at the end, the CLS token for the classifier and the separator token. And these tokens are what mapped to the word or string none, which we see when we print the output of word IDS. So tokenized input.word IDS will just print the these actual classes of the tokens. And that's a problem. That's why we got 11 for the length of the tokenized input IDs, but the original dataset contain only 9. And that's the problem we are trying to solve here in this method right here. Labels will be a new just a new list that will hold the labels later. And now I start the looping. NER tags, because that's the column name that the original dataset has, and that's what I am looping over. So here word IDs comes to rescue. The word IDS method in tokenized inputs. So my word IDS will be equal to batch index equal to I. So what this is doing is that word IDS will return a list of mapping the tokens and list of mapping the tokens to their actual word in the initial sentence, and it returns a list indicating the word corresponding to each token. And now I start my second loop. X over word IDS. So we have already seen the word IDS output will be something like this: none, 0, 1, 2, 3, 4, 5, 6, 7, 8, none. So this word IDS is just a list mapping the tokens to their actual word in the initial sentence, and that's what I'm looping over. And if word IDX is none, then set -100 as a label for these special tokens. Sorry, 1 second. And why -100? That's because again, this will be ignored by PyTorch during the training. Label IDS dot happened. Okay, and now if that is not the case, elif x is not equal to previous word index. That is, if the current word index is not equal to the previous word, then it's a most regular case, that is. And in that case, I'm just going to add the corresponding token of the word as it is. Label IDS dot happened label and word IDX. Why I'm getting label IDS is not defined, but oh yeah, so yeah, okay. And so two conditions are taken care of. I just have a last condition that is to take care of. So the last condition is for the subwords case, so we will see what it does. So this is to take care of the subwords which have the same word index. In that case, set it to -100 as well for them, but only if label all tokens, this argument is false. Otherwise, set it as it is. So in this case, label id as x else -100. Cool. And after these loops, I have to update my previous word index to make it equal to word in idx. Okay, come out of the loop, labels dot append, tokenized. So I'm just for the tokenized input, I'm creating a new key now, which is labels. Cool. And now I'm going to invoke this method. Why these extra spaces? Yeah. Tokenize. Train, I'm just taking from 4 to 5. Trained you. Okay, let's run from here. Cool. So this is output from the tokenized and aligned labels. So now just note one thing here, that if I printed the tokenized input variable before applying this method, then this dictionary will have only 3 keys, that is input IDs, then I will have token type IDs, and then attention mask. But after this method, a new key has been added in this line here, which is labels, and that's a new key that has been added to the tokenized input variable after the method, and that's the key whose values are properly aligned. All right, because we can see these 100 minus 100 has been added here for all the special tokens. Now let's print some of the tokens and labels to see them side by side. So I'm going to loop over tokenizer, Q, and a 0, Q, labels 0. Token. And also the label. What happened? Let me fix. Yeah. So here we can see the actual tokens and their corresponding labels. So CLS has -100, separator has -100. That's exactly what I wanted. All right. Tokenized data set now will be so again. Let's apply that method across the ConLL 2003 with the map function. It's a pretty powerful and pretty useful function from Hugging Face, where I can apply a particular method across all the input, all the elements, all the individual rows in a single line. Okay, and line labels. Cool. Now let's define my model. Auto model for token classification. From pre-trained BERT based on. Okay. Because we have 9 classes, so num labels equal to 9. Let it run. It may take a minute or so. Yeah. Cool. Okay. Now I need to define the training argument parameters. Transformers, import training arguments. Training arguments. And they are my training arguments. Let's run this cell. Okay, I also need to define the data collator. For token classification and pass tokenizer. So these data collators are objects that will form a batch by using a list of dataset elements as input. These elements are of the same type as the elements of trained dataset and eval dataset. And to be able to build batches, data collator may apply some processing like padding. Some of them, like some of the data collators, like data collator for language modeling, also apply some random data augmentation on the formed batch. So data collator actually automatically pads the model inputs in a batch to the length of the longest example. These bypass the need to set a global maximum sequence length, and in practice leads to faster training since we perform fewer redundant computations on the padded tokens and attention mask. My metric is seq-eval, seq-eval. Features and take the NER tags. Let's run it. Feature names, that would be, that's just feature.names, I think. Yeah. These are my feature names, okay? And now calculate these metric on a single example, and that example will be just this one. That is the very first element from the data set. And for that, what I need to do, I need to get the labels from that example. That is, label means the NER tags as a list. Label list I. Example NER tags. Yeah, So in the first example, I have these named entity recognition tags, that is B organization, O, B miscellaneous, etc. Now let's calculate the metric.compute. I'm passing the same labels to predictions and reference. And that's how you will get your result of the metric. And here I got the precision 1, recall 1, all these. The very ideal score is because I passed the same list to both my prediction and reference. But anyway, this was just for checking that metric.compute is working. And now I am going to define the actual compute metrics method, which will be passed to my training configuration. So the prediction logics will just be obtained by applying numpy.argmax, because the logics and the probabilities both are in the same order, so we do not need to apply softmax here, just the argmax. Right, logics across the axis of 2. And now I need to remove all values where the label is -100. Predictions. So before passing to the metric.compute, just as we saw here, I need to pass a list to both the predictions and the reference. To both this argument, I need to pass a list, and that's why here right now I'm going to do is create my predictions list and also the true labels list to be passed to the reference. Okay, now that will be prediction label list heads for a zipping of my prediction label if L is not equal to -100. Okay. Prediction label in zip, that would be between Fred logics and similarly true labels. Yeah, so this will be, I have to get my list element from the true labels. That means label list here, instead of eval preds this L for eval preds L and zipping of prediction and labels. So this label is my true label. So it's coming, this label is coming from these labels variables actually, what we defined here, and we will see that in a second for the next zip. If L right, prediction zip Let's name it predictions. Reference is and from this I'm just going to return a dict taking the various key values from my result, and that will be just this. Cool, that should work. And now I need to define my training configurations again in the next cells. So trainer equal to model, args training dataset is tokenized dataset, train tokenized dataset validation. So everything is defined. I can actually train my model right now. That is going to take quite a bit of time. I mean, if you are running in collab with GPU, it should not take more than maybe 6-7 minutes. I also need to write the code for saving the model. Save pre-trained. Tokenizer. Okay. And also need to define two variables here for converting my ID to label and label to ID. stri. That's my key here, and label list. Similarly for label to ID. For I, label in enumerate label list. Cool. And config. Sorry, import. NER model, because that's my model name. Just loading the config after the training. Remember this NER model here by this line, it's completely pre-trained, this NER model here is completely fine-tuned, because we started with the pre-trained model from Hugging Face, and then we trained it right here with this line, and after defining all the training configurations. So at this model, this NER model is coming from this model.save pre-trained, this line. So at this point, this is a completely fine-tuned model. And why I'm doing this? Because I'm going to test my fine-tuned model on a evaluation text, that whether that creates a proper kind of NER tags. Okay, and here config ID 2. That will be my ID to label. Similarly, config label to ID. These are all standard code. If you follow Hugging Face tutorial and their documentation, these are very much well written over there. Config.json w. Now load my fine-tuned model. So let's name it model fine-tuned. Auto model for token classification. Model. Okay. And So this is the output that you get for your this model fine-tuned. Okay, so a model config, BERT config, name or path NER model, architecture BERT for token classification, attention prob, dropout prob, all these ID2 labels are given here properly. Okay, so that's our fine-tuned model, and now I'm going to test this model on a example text. And there I have. First, I just imported pipeline so that I can use this pipeline method for getting the inference from my model. And then I'm just defining pipeline, passing NER for telling the pipeline that I'm trying to do named entity recognition. And for the model argument, I pass my model fine-tuned, which is my fine-tuned model. Tokenizer remains tokenizer. And for this is example text. Bill Gates is the founder of Microsoft. And all I do is NER result equal to NLP. And within that, I pass the example text. And this is my NER result. That is the inferencing from my fine-tuned model. And look at that. This first Bill Gates, it's obviously B person. A model has correctly predicted score with a score of 0.99. That is with a very, very high probability. Then word Bill, entity I person. Okay, so the first one was Bill, and that's this one, and the second one was this, and that's the word gets, and that's also I person. The next word is Microsoft, and that also it has correctly identified as beginning of organization with a very high score. So it looks like this inferencing, this was a very baseline inferencing. I just ran the training for 4 epochs, and it produced a very good result indeed. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.